Hello all. In this session, we will discuss the next CNN architecture, that is residual network, also called as ResNet. This ResNet was developed in 2015 by a group from a Microsoft research team, and they introduced a novel residual model architecture with skip connections. So the core concept behind this network is called as skip connection. The network also features heavy batch normalization for the hidden layers, thereby avoiding overfitting. And this technique allows very deep neural networks with 50, 101 and even 152 weight layers, which is more than that of the previous CNN architectures. Like VGGNet, we have talked about 19 layers, and in the previous session we talked about Inception module which had 22 layers. This ResNet module have 50 layers, 101 layers and even 152 layers. Though the number of layers of this network are very high, but it is less in complexity compared to that of the previous layers what we have discussed. And the error rate of this residual network is around 3.5% in this competition of ILS-VRC in 2015. This was the paper published by Keming He in 2015, and in this paper, this module of residual network was introduced, and this model was the winner of that ILS-VRC 2015 competition. And you can see a graph in this paper which represents that as we go more deep into the neural network, it becomes very worse because the error increases as the number of layers in the network also increases, which can be seen in these two graphs. X-axis represents the number of epochs or iterations, and on the y-axis you have the training error for the first graph and testing for the second graph. For 20-layer network, as the number of iterations are increasing, you can see there is reduction in the error rate. Whereas for the 56-layer network, though there is reduction in the error rate is very high. Training error rate of 56-layer network is very high compared to that of a 20-layer network. Whereas in the test error also, the same case, 56-layer network has very high test error compared to that of 20-layer neural network. So the concept of this residual network was introduced in that paper. The main idea or the main advantage of residual network is it will avoid the vanishing gradient problem that arises in a very deep neural networks by introducing skip connections, also known as residual connections. So you can see here different layers, input is being applied to different layers, and after all these layers you will have an output here f of x along with the original input, which is called as skip connection, which will be considered as the identity. So I will have here f of x, which is the output of all these layers, plus the original input x. So some additional operation is being performed here to obtain this equation, and we apply ReLU activation function into this. So when we have original input along with the layered output which is being generated after every convolutional and pooling layers, then there will be no question of vanishing gradient or vanishing exploding problem, because your output what is generated when you make f of x is equal to 0, your output what is generated will be same as that of the input, thereby increasing the accuracy of the model. These connections allow the network to learn residual mappings, effectively passing both the original input and the learned features to the next layer. So these f of x represents the learned features along with the original input will be generated here, so that if these learned features are also reduced to 0, output is equal to x, which is same as that of the input. That means my model is performing well. Coming to the features of this residual network, depth of this network is 50, 100 or even 150 layers, which is quite high compared to that of the previous CNN architectures like VGG with 19 layers and GoogleNet with 22 layers. Coming to the performance, builds on the success of previous deep networks like VGGNet and Inception, improving the feature extraction at many levels of abstraction, from basic edges to complex features. And the third feature is problem solving. This residual network helps in avoiding the vanishing gradient issue, which will be created whenever we talk about deep neural networks. And also overfitting will be avoided in these residual networks because it handles different regularization techniques like dropout, L2 regularization, and even batch normalization within the hidden layers. These vanishing and exploding gradient problems will be avoided by these residual networks, and we already have discussed what vanishing and exploding gradient is. Let me give you a quick recap of this vanishing and exploding gradient again. You know that W nu is equal to W old minus eta times of dou L by dou W old. The step size depends upon this value dou L by dou W naught, which is the gradient. When I have a deep neural network, in backpropagation as I am moving from one layer to another layer, the gradient dou L by dou W naught will be the multiplication of gradients of each layer, that is dou L by dou Y hat multiplied by dou Y hat by dou O3 multiplied by dou O3 by dou W naught. For example, if I take these three layers, obviously when I am moving back propagating from the output layer to the next layer, the gradient value reduces due to sigmoid and tan H activation function. That is, if it is 0.2 dou L by dou Y hat, the next will be obviously 0.18, which will be much less than this, and the third component or the third gradient will be much less than this, somewhere around 0.01. And when I multiply this dou L by dou W naught will be very small, thereby cancelling this term, so that there will be no updation in the weight. When I have no updation in the weight at this layer, the previous layers will get affected and thereby the training stops. This is called as vanishing gradient. Whereas in exploding gradient, when this dou L by dou W naught value is very high, which results in exploding gradient. When this value is high, this W nu will be updated depending upon this higher value. So when higher value of W naught is updated, it will oscillate from this point to this point but will not settle at the local minima. This is called as exploding gradient. These two problems can be avoided by making use of these residual networks. To solve this vanishing and exploding gradient, the scientist he created a shortcut that allows the gradient to be directly back propagated to early layers. These shortcuts are called as skip connections. They are used to flow information from earlier layers in the network to later layers, creating an alternate shortcut path for the gradient to flow through. Another important benefit of skip connection is that they allow the model to learn and identify the function, which ensures that the layer will perform at least as well as the previous layer. This is without skip connection, input is given to the first layer, output is fed as input to the second layer and so on. But when I introduce skip connection here, for example, this is the original input will be applied here. There is no question of vanishing gradient in this layer due to reduced gradient of that loss function. So you can see to the left side of the figure, we have a traditional convolutional neural network, and to the right side of the figure, we have skip connection, which is also called as residual connection. Note that the shortcut arrow points to the end of the second convolutional layer, not after it. You can see here. It is not pointed after that, it is pointed to the second convolutional layer. The reason is that we add both paths before we apply the ReLU activation function of this layer. And as you can see in the below figure here, the X signal is passed along the shortcut path and then added to the main path with f of x. This is the shortcut path, also called as the skip connection, added up with the learned parameter, that is the main path parameter, which is f of x, so that I get f of x plus x and then apply ReLU activation function onto this f of x plus x. Now when I introduce this f of x plus s, though the gradients are getting reduced here, I will be left out with the original input x here. So there is no question of vanishing gradient due to the introduction of these skip connections, also called as residual paths in the model. This figure represents all the three CNN, classical CNN architecture. This is the inception module, and these are the residual blocks which are being introduced, stacked one over the other. So this is the end of today's session. Thank you all.